Yeah, there we go. Floor is yours.
All right, thank you for the introduction and for, hi Karim. Wow, okay. Thank you for the introduction and for the invitation to speak. It's fun to be in Boston and Copenhagen and Jerusalem all at the same time. Okay, so I would like to tell you how many n-queens configurations there are. So I'll start by telling you what such a configuration is. And this goes back to a well-known chess problem. It's about 150, maybe even 170 years old. And the chess problem is, can you take 8 queens and place them on a chessboard so that none of them are threatening any other? So for those of you who don't know, chess is a game. It's played on an 8x8 board. And one of the pieces in the game is called a queen. And queens have the property that they can attack laterally along rows and up and down on columns, and also on diagonals in either direction. So they're like very powerful attacking pieces. And in a normal game of chess, there are usually only 2 queens, though there could be more. But in this riddle, there are 8. And you are to place 8 of them on the chessboard so that no queen attacks any other. So 8 is definitely the maximum possible, because you can't have more than 1 queen in each row. But indeed, it is possible to achieve this and place 8 queens on the board. And here are 3 solutions. So you can either look at them now or try to figure it out for yourself. It's, I think, not very difficult, but it's kind of fun. As mathematicians, of course, there's nothing special about the number 8. It's just the size of a standard chessboard. We very quickly will ask about the n-queens problem. We'll take an n by n board. And again, queens can attack along rows, columns, and diagonals. And we'll ask, can we place n mutually non-threatening queens on this board? So again, n is definitely the maximum because you can't have more than 1 queen in each row. And the first question that we'll ask is this possible? And the answer is that as long as n is at least 4, there's always at least 1 solution. So here's an example for when n is equal to 13. As combinatorialists, once we know that something exists, we often just want to count it. So we'll say that Q of n is the number of solutions to the n-queens puzzle, and then now we want to understand Q of n, and that's what this talk will be about. Okay, so I want to give some history, but before I do so, I'll just say that Natia is in the audience, and I'm his student, and I think he begins almost every talk by saying that the ground rules are that anybody is allowed to ask any question at any time. So just unmute yourselves and ask. I would rather talk about what you want me to talk about than just go on and on about something that nobody is following. So especially if anything is unclear, but also just any other question, just ask. Okay, so in terms of upper bounds, there's not much has actually been known until fairly recently. So the one very easy thing that you can say is that Q of n is definitely less than n factorial, because every n-queens configuration is in particular equivalent to a permutation matrix, because there's exactly 1 queen in each row and column, and there are n factorial permutation matrices. So Q of n is less than n factorial, and I'm writing n factorial in this funny version of Stirling's approximation, n divided by e to the power of n, because this is the form that basically all of the other bounds that I'll mention today take. So that's an easy upper bound. Then there's a not so easy upper bound, and I'll say a little bit about how you do this later in the talk. So Toroidal, about I guess 4.5 years ago at this point, proved that Q of n is at most n divided by e to something bigger than 1 to the power of n, and this uses the entropy method, or the Radhakrishnan linear Luria entropy method, which will feature prominently later in the talk. In terms of lower bounds, a little bit more was known, kind of historically. So there's like this, there are letters in which Gauss kind of lists 72 solutions to the 8 queens problem. There are in total 92 solutions. So Gauss didn't find all of them. And there's this story, which is probably apocryphal, that Gauss actually claimed that Q of 8 is equal to 72, which he would have been wrong about. But it seems like this is probably not historically true. We just maybe spent an afternoon on it, found 72 solutions and then moved on. But at any rate, the fact that Q of n is always positive for sufficiently large n, in this case 4, was proved probably in 1874 for the first time. And then there are not so many bounds, so many constructions. This Paul's construction gives basically one solution, or maybe is O of one solutions anyway, once you can't account for symmetries for each n. In 1994, Riedenwaldi and Zimmerman showed that Q of n is at least something exponential. And actually, n has to satisfy certain arithmetic conditions. So they showed this for a dense set of integers, but this is actually not true according to their bound for all integers. And then for a different set of integers, but for infinitely many integers, but not all of them, Luria showed in the same paper that I already mentioned, the super exponential bound of n to the power of n over 16. And so this was basically the best that was known until just a few months ago. I should mention that the last two bounds, so I mentioned that they have to satisfy some arithmetic condition. They're actually lower bounds on something called the toroidal or modular n-queens problem, which I'll say quite a bit about soon. But this is a version of the problem where the diagonals wrap around the board. So they don't end when you get to the top of the board. If you follow a diagonal to the top of the board, you can keep following it from the same spot in the bottom of the board, kind of like an old DOS game from the 80s. And the toroidal version is has a much more algebraic flavor. It's much more symmetric. So I think often when I've told people, mathematicians, that I'm working on the n-queens problem, they immediately ask, well, are you working on the toroidal version? Which I actually have not been working on so much. But most lower bounds up till just a few months ago were for the toroidal version, which exhibits much more symmetries and maybe one would think is easier to work with. Anyway, the main result that I want to kind of talk about today is the following bounds on Q of n. So there exists a constant beta, which is about 1.94, such that Q of n is equal to some error term times n divided by e to the power of beta, and all of this to the power of n. So this is both a lower and an upper bound. This constant beta is probably doesn't have a nice form. It's characterized as the solution to some convex optimization problem. And these bounds on beta are found by either witnessing a lower, well, I guess it's a concave optimization problem. So either witnessing a lower bound on the maximum or kind of using duality to obtain an upper bound on the maximum. But at any rate, the optimization problem itself is not that difficult to understand. So it does give some explanation for this bound. Okay, so now would be a good time for questions. And if there are no questions, I'll just kind of say a few words about how I see the n-queens problem as fitting into kind of the last few years of action in a field called combinatorial designs. So a combinatorial design, kind of very broadly, is a hypergraph that exhibits some sort of regularity property. So it's not very well defined, but here are some examples. So regular graphs are in particular hypergraphs with a regularity property. What Nathi calls high-dimensional permutations. So the simplest example of this is a Latin square. So here on the left, we have a 3 by 3 by 3 matrix, where in each row or column or shaft, there's exactly one black square, and all the rest of the squares are white. So this is, you can see how this would be a high-dimensional version of a permutation matrix. So this is again a hypergraph exhibiting a regularity property. And another kind of very famous version of this are Steiner systems, of which probably the simplest example is Steiner triple systems. So a Steiner triple system is where you take n vertices and you find a set of triples such that each pair is contained in exactly one triple. And here at the bottom, there's the Fresnel plane, where I have 7 vertices, and I've divided them, kind of, you can follow the colored lines, into triples, such that each pair is contained in exactly one of these triples. So this is an order n-Steiner triple system. So kind of the n-Queens configurations, I'll say a little bit more about this in a minute, but you could kind of see how they are hypergraphs or graphs maybe with some sort of regularity. I mean, they're permutation matrices with an additional constraint. So they sort of fit into this framework, but not quite. Okay, so there have been a lot of breakthroughs in the area of combinatorial designs in the last few years. So here are a few. This is mostly name dropping. But we have the entropy method, which allows us to find upper bounds on the number of combinatorial designs. We have randomized algebraic constructions, which were introduced by Peter Kivash. And these actually gave the first proof of the existence of Steiner systems, which was actually not known except for very specific sets of parameters until just a few years ago. This is a very powerful combination of the probabilistic method and algebraic constructions that can be used to construct combinatorial designs. Then there are other absorption methods, in particular what's called iterative absorption, due to the Birmingham group headed by Daniela Kuhn and Derek Ostus. And they gave a second proof of the existence of designs, but also of other very powerful construction theorems in combinatorics. But kind of all of these methods rely on the underlying problem having some very strong form of symmetry, which is usually the case in combinatorial designs. But the n-Queens problem doesn't quite have this because the diagonals have different lengths. So the problem is not quite so symmetric. You can't like interchange spaces on the boards just at will because the constraints will be different. All of a sudden there will be more or less kind of threatening positions if you look at one space versus a different one. So kind of these methods seem like they might work, but they kind of run into challenges. So today I hopefully will tell you a little bit about how to overcome these challenges, at least with respect to the n-Queens problem. So I've already mentioned the toroidal version, and I'll say a little bit more about it because of its symmetry, it's kind of easier to work with at first and to understand where the difficulties with like kind of the classic n-Queens problem kind of come in.
Sorry, Michael, there is a small question in chat by Karim.
Oh, sorry, I'm not.
Yeah, no worries. That's why I'm doing it. That's good. But Karim asks that maybe they work in the toroidal case. So the methods you just mentioned.
So okay, I mean this is an excellent question, and just wait for the bottom of this slide and you'll have your answer.
Okay.
Okay. So yeah, so I've already mentioned that the toroidal case is this case where the diagonals wrap around the board, and it is much more symmetric. So this certainly does seem to fit, as Karim intuits, into the framework of combinatorial designs. So we're going to say T of n is the function that counts toroidal configurations. Now definitely any lower bound on T of n will also be a lower bound on Q of n, because every toroidal configuration is in particular an n-Queens configuration. So kind of a pretty simple application of what's known as what I call the entropy method, but it was pointed out to me that there are many entropy methods and I should be more specific. So if I ever say the entropy method in the remainder of this talk, what I mean is a method that uses entropy that was developed by Radhakrishnan for permanent bounds and extended by Nathilinia and Suoluria for more general bounds on designs. So Suoluria uses this method to show this bound on T of n. It's at most n over e to the 3 to the power of n. And we're actually going to prove this in a few minutes because it's a very nice proof and it's not that difficult. And it really gives you a feel for how these things work. Now, had I given this talk 2 weeks ago, this would have said conjecture, this is tight, that T of n really should be equal to n over e to the 3 to the power of n. But just about, I think exactly 2 weeks ago, Candy Boughton and Peter Kivash of the University of Oxford posted a preprint on arXiv that proves this. So I have not had time to fully digest their proof. Their paper is 162 pages long, but it uses some combination of two methods that I've mentioned, the randomized algebraic constructions and iterative absorption to get this lower bound. So I guess the answer to Kareem's question is yes, these methods do turn out to work for the toroidal version. But by the way, if you'd like to hear more about this proof, then I invite you to the Harvard CMSA Combinatorial seminar, where Candy Boughton will be speaking about it in a few weeks. Anyway, so what I'm going to do now is, as promised, I'm going to prove the upper bound on T of n. So again, this would be a good time for questions before I start talking about the entropy method. Okay, so here's a little bit about entropy. It's likely that most of the people in the audience already know these things, but since I want as many people as possible to understand the proof, I'm going to just tell you a few basic properties about entropy. So the setup is that you have some random variable x that takes values in a finite set S. So its entropy, denoted h of x, is this function over here, some sum over something. And here are some basic properties. So the entropy of x is always less than the natural logarithm of the size of S. That's the set in which it takes its values. And equality holds if and only if the distribution is uniform. Now we also have a concept of conditional entropy. So here the setup is you have a pair of random variables that take values in a product space. So the conditional entropy of x given y is the expected value of the entropy of x, where the expectation is taken over possible values of y. So kind of intuitively, entropy is the amount of information that you are likely to need or that you expect to need in order to communicate the value of this random variable x. And conditional entropy is the amount of information that you expect to need to communicate x if the party you're communicating x to already knows what y is. And the distribution in both cases is public knowledge. And then the final property that I need is something called the chain rule, which says that, well, if I think of xy as its own random variable, then it has its own entropy. And then the entropy of xy is equal to the entropy of y plus the conditional entropy of x given y. Okay, so these are basic properties of entropy. Yeah, and now I'm going to switch to, my writing pad, where it's much easier to give proofs. And I'm going to prove this bound on the number of toroidal n-Queens configurations. T of n is less than basically n divided by e to the power of 3 and all this to the power of n. Now, my handwriting is not the best under normal circumstances, and over the internet it's probably worse. So if I write anything unclear, just tell me. Here's what we're going to do. We're going to say, let x be a uniformly random toroidal n-Queens configuration. So based on what I know about the entropy method, the entropy of x is equal, because it's uniformly distributed, to the logarithm of T of n, the number of configurations. Now, I'm going to say, well, let x1 to xn be a uniformly random ordering of x. So what I mean by this is x is a toroidal n-Queens configuration. So it's actually just a set of queens, right? Or a set of coordinates on the square. And there are n of them, because by definition, that's what a configuration is. So take these n-Queens and just order them uniformly at random. Now I get these new random variables, x1 to xn. And there is a relationship between the entropy of this kind of n tuple of random variables and the entropy of X, it is the following. So in order to get x1 to xn, you can think of this really as taking kind of distribution in a product space. I took X and I took a random permutation. So the entropy of doing that is h of X plus the logarithm of the number of permutations, because these things are independent. And then this is enough information for me to just get x1 and xn, because kind of the random permutation tells me in what order I should look at the x's. So any bound on h of x is going to be a bound on t of n, and also any bound on this n tuple will be a bound on t of n, or rather the entropy of the n tuple. So now I'm going to use the chain rule in order to calculate this.
Sorry, Michael, sorry, can I ask again, what is the uniformly random ordering of X? I didn't follow that.
Sure. So just because your name didn't pop up, could you tell me who asked?
It's Ron Pellet, sorry.
Okay, yeah, hi, Ron. Sure, so X is a toroidal n queens configuration. So it's really just a collection of, say, n coordinates on the n by n grid, right? So take these coordinates and order them uniformly at random. Okay.
So you think of each queen as a pair of integers between 1 and n, telling us where the n by n board, and you take the vector of length n of pairs and you reorder it?
Yes.
Right. Okay, thanks.
Okay, great, thank you.
So if I may, just for me to make sure, is this equivalent to just giving labels to the queens and in the end kind of forgetting about them again, right? So you
I think so. Like if the labels are kind of.
So you could also talk about labeled queens, and then you would just get n factorial times the thing you want, right?
Yes, I think so.
Okay.
I mean, the labels would be like kind of an ordering.
Yeah.
And if you say this is the first queen, that's the second queen, etc.
Yeah. Okay. Good. Thanks.
Right. So just to be crystal clear, hopefully, every specific n queens configuration can be ordered in n factorial ways. And then I'm just drawing one of these orderings uniformly at random. Okay. So kind of using the chain rule inductively, in order to find out the entropy of this tuple, it's equal to the entropy of xt given x1 to x t minus 1. And now we're going to spend some time thinking about this guy. So kind of what this is telling me, or what I'm trying to understand here when I'm looking at the entropy of xt given kind of the previous queens in the sequence, is how much information do I need in order to specify the tth queen in the sequence if I already know t minus 1 queens. So let's think of like the following process, which is basically what is going on here. What happens is that I've drawn my n queens configuration uniformly at random, and I'm revealing the queens one at a time in a uniformly random order. So here's my board. And I've revealed 1, 2, 3 queens. And now I'm about to kind of reveal x4. So I'm going to pause. I'm going to say, okay, well, if I've revealed a queen, then I know that x4 is not going to be here, or well, there, or there. And because it's toroidal, also not there. And also not in this row, or that column, or that diagonal, or that one. Yeah, pardon me, these diagonals should definitely not intersect. They are actually supposed to be straight lines in some sense that are parallel to each other. Okay, so kind of the red areas of the board are places where I know for sure that the next queen is not going to be, because of it has to satisfy this constraint of queens cannot attack each other. So I'm going to call the rest of the areas of the board, A, okay, that's supposed to be like a fancy A of t, A for available. These are the available positions at time t, meaning after I've revealed t minus 1 queens, the next queen definitely is going to be in the set xt. So if xt is distributed here, then I know that its entropy is at most, well, the logarithm of, well, so here A of t means the cardinality of this set fancy A of t. But so again, because when I have a random variable, its entropy is always less than the logarithm of the size of the set in which it takes values, I get this inequality, but because it's conditional, actually the correct thing to do, kind of when you work through the definitions, is to put an expectation here. Okay. So A of t is a random variable. It's the number of available entries at time t, and then log of A of t is a random variable, and I can calculate its expectation. But because the logarithm is a concave function, this is less than the logarithm of the expected value of A of t. And now I'm going to kind of try to say something about this person, the expected value of A of t. So one thing that I know is that because the board is, I'm talking about the toroidal configuration, the board is very symmetric. Like there's no way to differentiate any particular place on the board from any other. So whatever the expected value of A of t is going to be, it's definitely going to be n squared times something. And the something is going to be the probability that a specific square on the board is still available at time t. And now, how can we calculate this? Well, what I'm going to need is, here's a square on the board. I want to know what the probability is that it's available at time t. And I know that since I'm in a toroidal configuration, there is a queen in its row, and, sorry, in its column, and in its row, and in each of its diagonals. These queens may or may not have been revealed at step t in the process. If any of them has been revealed by step t, then the square in the middle is unavailable. But if none of them have been revealed by time t, then the square in the middle is available. So you kind of have to do a little bit of arithmetic here, but essentially the correlations of the probability of revelation of each of these 4 queens are very, very small. So this something is going to be something to the power of 4, and something is going to be the probability, more or less, that a specific queen has been revealed sometime in the first t steps of the process. Okay, so now what I'm going to do is I'm just going to plug this thing into there, and then this into there, and this into there. And this will allow me to obtain a bound on h of x. So the arithmetic I'm going to do rather quickly, because it's not the most interesting part, but now we have that. So the sum of h of xt given previous revelations is at most the logarithm of the expected number of available positions, which is this, more or less. So I'm kind of ignoring small error terms. And this is equal to, well, 2n log n plus n.
You forgot the sum, Michael. You forgot the sum in the previous line. Sum of the logs.
Thank you. Of taking the 4 out of the log, then I get this. And if I have a keen eye, I'll notice this is actually a Riemann sum for the integral from 0 to 1 of log 1 minus x, which is equal to minus 1. So what I'm getting from all of this is 2n log n minus 4n. And if I plug this back up in here, what I'm going to get is the entropy of x is equal to 2n log n minus 4n plus, minus the logarithm of n factorial. Now the logarithm of n factorial using Stirling's approximation is n log n minus n. So this is equal to n log n.
Michael, sorry to be a nag, but less than
Yes.
H.
Thank you. Absolutely. And because I'm ignoring error terms here, there's maybe something small that you have to add here also that I'm not writing at all. But this tells us, well, the nut t of n is equal to e to the h of x, which is now less than 1 plus some error term, n over e to the 3 to the power of n. Okay, so that is the entropy method proof of the upper bound on T of n. Okay. If there are any questions, before I go back to my slides, now is once again a good time. Okay, so I hope you enjoyed that proof. Here's what we know about the lower bound, which again, these slides were kind of changed over the last 2 weeks because we actually do know that this is a lower bound. So here's this lower bound theorem. T of n is greater than, okay, so I see that I forgot to write the error term inside, but it's essentially n divided by e to the power of 3 to the power of n. Now, toroidal configurations only exist when n is equal to 1 or 5 modulo 6. So that's this kind of parenthetical about arithmetic conditions. Now, here's how you would go around proving the lower bound, kind of using standard techniques. The paradigm would be something called random greedy or nibble plus absorption. So run a random greedy algorithm for the toroidal board. So what this means is, what you want to do is construct a toroidal n-queens configuration using a randomized algorithm, and you want to count the number of choices that the algorithm makes, because this will tell you how many possible outcomes it can have, and each outcome is a toroidal n-queens configuration. So this will give you a lower bound. So a random greedy algorithm means start with an empty board, choose a place uniformly at random, and put a queen on it. Now, some of the places on the board are unavailable, but look at the remaining available places, choose one of them uniformly at random, and put a queen on it. And keep going, hopefully until you obtain an n-queens configuration. Now, you probably won't actually obtain an n-queens configuration. You will get stuck, but it's not so difficult to show, kind of using a martingale analysis, that with very high probability, you won't get stuck until you've placed at least, say, n minus slightly less than n, like n to the 0.99 queens on the board. So almost all the queens will be on the board by the end of the random greedy algorithm. And furthermore, you can control the number of choices that you have at each step. It will be approximately n squared times 1 minus t over n to the power of 4. Now, you might recognize this term from the proof of the upper bound. This was actually the expected number of available positions after t steps of the process. Okay, so if you now kind of multiply the number of choices you had at each stage, which is basically the same calculation that I just did, except without the logarithms, then you'll come to the conclusion that there are this many possible outcomes of the random greedy process, but actually each outcome of the random greedy process gives you an ordering of the queens, because the queens were placed on it in a particular order. So you're going to have to divide the number of outcomes by n factorial. And then you'll get a lower bound of n over e to the 3 to the power of n. Now, what have I kind of skipped is the fact that this random greedy algorithm actually doesn't produce a toroidal n-queens configuration. It produces maybe an approximate configuration, but it'll have almost n queens on the board, but not quite n. So something additional has to be done. So kind of the second to last bullet just says, well, okay, take the outcome of the random greedy process and complete it somehow. placed a few more queens on it to obtain a complete configuration. And it turns out that this can be done. This bullet kind of hides in it 150 pages of detail from Kivesh and Beltel's proof. Had I given this talk 2 weeks ago, I would have said, well, I just don't know how to do this. But this is basically what the proof looks like, and all the work goes into proving the second to last bullet. So, all right, so that's all I'm going to say, I think, about the toroidal problem. But back to the classic problem, it turns out that this paradigm is basically what you need to lower bound the number of solutions to the classic problem. So now we're trying to prove something else. Now we're going to prove that Q of n, the number of solutions to the classic problem, is at least n divided by e to the 3 to the power of n. And this is a theorem of mine, together with Toluria in a preprint that we posted last May. And Kivesh and Beltel's proof basically uses different methods, but also as a corollary gives the same result. So they have their independent proof of this. So the proof is going to be exactly the same as what I just said, except that when I get to the second to last bullet and say, complete the outcome to obtain a configuration, all of a sudden I remember that although I've been running the random greedy algorithm on the torus, actually I'm trying to construct configuration, like classical configurations. So this gives me a little bit of extra flexibility when I'm doing the completion step, and I'll show you how. So the outcome of this, it's not difficult to complete the outcome of this algorithm to a classical configuration. Here's what you do. So here's the algorithm, n equals 15, and I'm just placing queens on a board uniformly at random, subject to the toroidal constraint. And I've been very lucky. I've managed to place 14 queens on the board, but of course I want 15. So at this point I'm stuck. Okay, there is an empty row and an empty column, but I can't put the queen that I want to in their intersection because it'll conflict with diagonally with previously placed queens. So what I'm going to do, I'm going to actually take a step backwards. I'm going to remove this queen up in the second row. It's gone. So now there are only 13 queens on the board. So I've made my situation worse, maybe. But actually, my situation, in fact, has improved, because if there are 2 empty rows and 2 empty columns, then there are 2 ways to fill them with queens. I can go for the kind of northeast and southwest corner, which I already tried, and I know it doesn't work. So I'm going to try the northwest and southeast corner, and luckily, this works. Okay, so there are no diagonal conflicts, and now I have 15 queens on this n by n grid, and I've obtained the solution to the classical problem. So this is a very simple instance of like an absorbing technique where you have some combinatorial structure that you can use to kind of absorb into it additional things that you want to add. And I won't say much about kind of the proof of why you can do this absorption. The intuition, though, is pretty simple. So like kind of like the key observation is that as opposed to the toroidal case, in the classical case, there are n queens on the board, but actually there are approximately 2 times n diagonals in each direction. So even in a complete configuration, half of the diagonals are going to be empty. So if you choose a diagonal uniformly at random, with probability about 50%, it'll be unoccupied. And if you choose 4 diagonals uniformly at random, so it won't be quite probability, well, I mean, I guess that will be probability 1/2 to the 4th. But if you do the following trick where you kind of say, I want to add the queen in the southwest corner here, but I can't. So I'm just going to remove a different queen that I choose at random. Then kind of the diagonals passing through the opposing corners are also somehow chosen at random. And it turns out that with positive probability, bounded away from 0, this trick will actually work. If you remove a queen uniformly at random, you'll win by being able to place 2 queens in the opposing corners. Okay? So this is how you can prove a lower bound on Q of n of the form n over e to the 3 over n. You nibble or run a random greedy algorithm on the torus and then complete on the classical board. So I'm not going to say anything more about this completion step. It will be used again when I prove kind of the more correct or the better lower bound on Q of n. But kind of the focus won't be there. Okay. So now that we've talked a lot about the torus and how to move from the torus to the classical board, we're going to try to really understand the additional difficulties that are presented by the classical case. So kind of one of the, probably the crucial detail of the analysis of the torus was that because every board position in a toroidal configuration is threatened by 4 queens, one in the row, one in the column, and one in each diagonal, this is exactly what allowed us to write this A of t is expected to be about n squared times 1 minus t over n to the 4th, which was like kind of like the crucial thing when we did all our calculations, both in the upper bound and in the lower bound. But in the classical problem, this is simply incorrect. So because of this thing where you have, you know, a lot of unoccupied diagonals, half of them, not every board position is threatened by 4 queens. It will always be threatened by a queen in the row and column, so at least 2 queens, but then it could be threatened by 0, 1, or 2 queens diagonally. So every queen will be threatened, either 2 threatened, 3 threatened, or 4 threatened. And kind of these 2 diagrams on the bottom are, well, in the left one, I've taken just a random 50 queens configuration. So like kind of like the dark red spots are the queens. Those are pixels are the queens. And then I've shaded the remaining pixels on the board depending by how threatened they are. So the brighter spaces that are kind of clustered more in the middle, the bright yellow ones, are 4 threatened. They have queens in both of the diagonals. Then towards the corners, you see the lighter brown ones, which are 3 threatened. And kind of beside them, you see a few spaces that are even darker brown, which are only 2 threatened. Both of their diagonals are unoccupied. Okay, so on the left, you see this for order 50, and on the right, it's for an order 1000 and queens configuration. And kind of this fact that you have 2, 3, and 4 threatened queens prevents us from writing something as simple as the expectation of the available positions is, you know, some very nice expression. But you can hope to do the following. You can say, well, maybe I'm told ahead of time. I want to apply, say, the entropy method. And I'm told ahead of time that for I, each of 2, 3, and 4, there are, in the eventual configuration that will emerge, right? So remember, the entropy method is you take a random configuration and you reveal its queens in a random order. And I'm promised that in the eventual configuration, there will be DI, I threatened positions. So if I know this, then I could write that the expected number of available positions after t steps is approximately some not too horrible expression, you know, some sum over I of DI, the number of I threatened positions, times the probability that an I threatened position will still be available at time t. Okay. And then you can do, well, the following trick. So, I mean, at this point in time, we don't really know how many I threatened positions there are in like an arbitrary n queens configuration. This could actually vary quite a bit. But for every vector of d2, d3, d4, you obtain an upper bound. And then if you maximize over all these vectors, you will get a universal upper bound on the number of n queens configurations. And you can do additional tricks because d2, d3, d4 can't be just anything. I mean, one obvious constraint is that their sum has to be basically n squared. But there are maybe additional structural things you can say about how queens can be placed on the board to give it kind of better bounds. And this is something that Soloria did in 2017, the same paper that's already been mentioned a few times. And he was able to obtain an upper bound of n to the power of e to the essentially minus 1.58, the power of n, where he kind of identified some non-trivial constraint that d2, d3, d4 have to satisfy and then optimized for that. And you get this. So this is very nice. It's the first non-trivial upper bound on Q of n, but it's not quite enough to kind of find the truth. But using this sort of idea of looking at I threatened positions for 2, 3, and 4 will play a role. Okay, so what I'm going to do now is I'm going to sketch out how you might get an even tighter upper bound on Q of n. So in the previous slide, I said, well,
may I
suppose
ask something very basic?
Yes, but just tell me your
maybe?
name, because for some reason
Itai.
Itai, yeah.
I don't know why, but I'm not getting why there can be a position that is only threatened by 2 directions. I can understand why 3, because if you're in a corner, then you don't have one of the diagonals, right? Because it's just you in the diagonal. But how 2?
Right. So I mean, if you look at this configuration, okay, this position. So okay, there are only 13 queens on the board, but that's not actually the issue here. This position does not share either of its diagonals with a queen, right? The long diagonal passing through it is actually unoccupied. And the reason why that's possible, even in a complete configuration, is because there are twice as many diagonals, because I'm not working on the torus. Like there are n diagonals that start on the top of the board, and then it's basically another n that start on the right of the board. So there are n diagonals, but only, sorry, there are 2 times n diagonals, but only n queens. So only half of these can be occupied. So all I need to find like a 2 threatened position is for one of these unoccupied diagonals to intersect with one of these unoccupied diagonals.
When you talk about whether a position is threatened, you mean when you already have some queens on the board, or do you mean in general?
Well, so I think
how many?
So like in this slide, I was referring to like in the final configuration after I've already placed 15 queens on the board. Yes, there are queens on the board, and I'm referring, I understand your question now. Yes, there are queens on the board, and I'm asking whether, given these queens that are already on the board, which possibly could even be a complete configuration, is a particular position threatened by X number of queens in this particular configuration.
Okay, thanks.
Okay, yeah. Okay, thank you for that, yes. Okay, so now in the previous slide, I said that, well, I'm only looking at configurations that, you know, where I'm promised that there are DI threatened positions. Now I'm going to do something like even more specific. I'm going to look, instead of the set of all queens configurations or the set of all configurations with a guarantee on DI, I'm going to say, now I'm dividing my board into these diamonds. Okay? And I'm indexing the set of diamonds by kind of curly I. This is how I learned to write an I in grade school. And then there's a function gamma, which is just a probability measure on these diamonds, right? And I'm restricting myself to configurations that have the following property. For every diamond alpha, the number of queens in alpha is equal to, or maybe approximately equal to, gamma of alpha times n. So in other words, I'm looking at, and I should say, so what I've done here is, you know, kind of, it's not clear exactly where the grid of queens comes into play. So the idea is I have this square with its division into diamonds, and I take my queens configuration and I overlay it. And then I can count how many queens fall in each of these diamonds. And right now, for the next few minutes, I'm only interested in queens configurations with this property, that the number of queens in each diamond is equal to gamma of alpha times n. And I'm going to show that I can obtain what turns out to be a tight upper bound on the number of such configurations. And this will be kind of the key to eventually getting the right upper bound on Q of n. So I'm going to use the entropy method again. Let X be uniform, random, queen configuration satisfying that condition. And as before, x1 to xn is a uniformly random ordering of X. So I'm thinking of the following process. I draw X uniformly at random from the set of queens configurations that satisfy this constraint. And then I order the queens in X uniformly at random, and I start revealing them one by one. So as before, what I'm going to want to bound ultimately is the entropy of xt given the previous queens in the sequence. This is what is going to feed into my eventual my upper bound on the number of such configurations. So let's like think what could happen here. I'm actually going to introduce an auxiliary, another random variable, which I'm going to call yt. And yt is equal to the diamond alpha such that xt is in alpha. All right, so yt actually, it's an additional random variable, but it's entirely determined by xt. If I know what xt is, then I know in which diamond it is, so I know what yt is. But the converse, of course, is not true. If I know what yt is, then I just know that maybe the next queen is going to be in this diamond, maybe. But this doesn't tell me exactly what the next queen is going to be. But using like the chain rule again, I can say that the entropy of xt, given the previous revelations, is equal to the entropy of yt, given what you know so far, plus the entropy of xt, given what we know so far, and also given the knowledge that xt is going to be in the diamond yt. So I've broken up this entropy into two pieces, and now you can think of the following kind of multi-stage process, where first I draw my configuration uniformly at random, and I start revealing the queens. But before each time I reveal a queen, I actually send you two pieces of information. First, I send you in which diamond the next queen is going to be, and then I tell you which queen specifically it is. All right, so how does this help us? So first of all, this first term is fairly easy to understand because what I have is a queen's configuration where I know what the distribution of queens into diamonds is. So I know basically what the probability that at step t, the queen is going to be in a particular diamond is. Okay? It's basically gamma of alpha, even conditioning on previously revealed queens. It's basically gamma of alpha. So the entropy of yt, even with this conditioning, is essentially equal to the entropy of gamma. So this is kind of easy to understand. And then this turns out also to be not too difficult to understand. So what I can start doing is, well, I say, okay, I know how many queens are in this diamond and in this diamond and in this diamond. So I know how many diagonal threats into this blue square or blue diamond are coming in this direction. I also know how many diagonal threats are coming from this direction. All right. So, and now I'm about to lie, and we'll see if anybody calls me on it. But every diagonal thread coming from here intersects each diagonal thread coming from here in exactly one position. So this position in the intersection is going to be 4 threatened. So now I know how many 4 threatened places there are. I also know how many 2 threatened places there are because those correspond to like non-threats in this diagonal intersecting non-threats in this diagonal.
You're talking about black and white, right?
Yes. So thank you, Nati. But you've maybe heard this before. I don't know. Yes. So I'm lying because it's simply not the case that every kind of plus diagonal intersects every one minus diagonal. It depends on some parity condition because black diagonals never intersect white diagonals. So in the actual proof, this is surprisingly like not a minor thing. You actually have to spend quite a bit of time dealing with this. But the intuition is that the entropy is maximized when kind of these threats are assumed to be independent. And then you just say, well, every plus diagonal intersects every minus diagonal with 50% probability, and that gives you the right bound. But it's a more complicated story to tell. Anyway, the point is, using such considerations, I now know how many 2, 3, and 4 threatened conditions are in positions are inside the square. And then, using what I had on the slide already, I can write some expected value for the number of expected positions here. And this, once you do some arithmetic, gives you some bound on the number of configurations satisfying this constraint. And I'm going to spare you kind of working out the details, but what you end up with is this. So ignore the definition. I'll move back to that in a minute. What you end up with is, if you have this gamma, that was the distribution of places on the board, and then you end up with an entropy function that governs the number of n-queens configurations that are distributed according to gamma. And it has a few contributions. So it has a KL divergence term of gamma versus the uniform distribution on the square. And then it has another two, there's a typo here, but it has another two KL divergence terms corresponding to gamma plus and gamma minus, where these are, okay, well, given gamma, we know what the distribution is on occupied diagonals. That was this thing that I drew over here. And this distribution on occupied diagonals gives can be thought of as a distribution basically on the interval -1, 1, where -1 is in the upper left corner, 0 is in the upper right corner, and 1 is in the bottom right corner. And then, well, if it's a distribution on -1, 1, you can look at its KL divergence with respect to uniform distribution. And when you do the arithmetic that I just kind of like outlined, these are the terms that pop up for the entropy of this random variable x, which gives you the upper bound on the number of such configurations. And in general, you can do this for something that I call a queenon, which is a limit object for n-queens configurations. So it's, without like giving you like the exact definition, it's a Borel probability distribution on the square. And then you can ask, well, how many n-queens configurations correspond or distributed similarly to this particular probability distribution on the square? And the answer is governed by this function, HQ of gamma. Okay. So this tells you about upper bounds, but I haven't said anything about lower bounds. But for lower bounds, actually, it turns out that you can basically reverse this process. So what is this process? I've drawn a queen configuration uniformly at random, and then I've started revealing its queens in a random order. And I know that they follow this distribution gamma. So if you, the viewer, if you did not know that all I was doing was just relaying to you the information that I got by drawing a queens configuration uniformly at random, you might mistakenly think that what I was actually doing was the following process. Start with an empty board, draw a diamond alpha according to this distribution gamma, and inside that diamond, choose uniformly at random an available position and place in it a queen. And then you would see before your eyes the same thing. You would see a queen's distribution kind of being constructed, one queen at a time. And it turns out you can analyze this process and it will succeed with very high probability in placing almost n queens on the board. And once you have an approximate configuration with almost n queens, you use an absorption trick, the same one that I showed you before, to complete it to a complete configuration. And the point is that this construction process has the same entropy, more or less, as the upper bound, where we weren't constructing an n queens configuration, we were just revealing one queen at a time. And so what you conclude is that the number of n queens configurations matching this distribution is actually basically equal to some term depending, sorry, I skipped too much forward, just concentrate on the theorem on top, some term depending on this entropy function. So like if I take a queenon, a distribution gamma, and a natural number n, and I ask, well, what is Bn of gamma epsilons? This is the number of n queens configurations that are, well, I haven't defined this properly, but that are kind of distributed similarly to gamma. So the answer is, well, it's n times e to the power of h q of gamma to the power of n, more or less. Okay, and then you need to do some additional kind of acrobatics, but nothing too difficult. To understand this function HQ, it turns out to be concave or strictly concave, so it has a unique maximizer, and it's defined in a compact space, which is useful for getting upper bounds. And the eventual theorem you end up with is, well, if I have a concave function that governs the number of Queen's configurations, then, and I want to know how many there are, then what I should do is maximize this function, has a unique maximizer gamma star, and then the number of configurations is approximately n times e to the HQ of gamma star to the power of n. And this HQ of gamma star is approximately 1.94. So that's how we know the number of n Queen's configurations. Okay, there's kind of one other very nice thing, which is that this method actually tells us that not only do we know how many n Queen's configurations there are, we actually know what most of them look like. So most of the n Queen's configurations will be distributed similarly to gamma star. And here is gamma star. This is what I've done is I've discretized the optimization problem to a 50 by 50 grid and found the maximum numerically. And then it looks like this. This is interesting because it's a very non-uniform distribution. So like this is maybe not unexpected, but it really was not obvious to me for a very long time while I was working on this problem, that a random n Queen's configuration does not look at all like a random permutation. Random permutation is fairly, or permutation matrix is fairly uniformly distributed on the square. And this is just not true for n Queen's configurations. They look more like this. Okay, so here is my backup slide in case the animation didn't work. And I'll just say that, so this bound on Q of n, I think like in terms of proofs, this is like by far the best bound that has been given so far. Like all previous bounds were basically, well, there were actually essentially no non-trivial lower bounds that worked for all n. But empirically, this problem has been studied. So here's like a physics paper from about a little more than 10 years ago, where they used Markov chains to kind of estimate the number of n Queen's configurations there are. And so kind of what I've highlighted in red here says, well, this 0.944 corresponds to what I wrote before as 1.94. So they got a very accurate estimate for Q of n using empirical methods. So this maybe was kind of known, has been known for a little bit. But now we know that this is also not only known, but it's also known to be true. Okay, so that's all I want to say today. And thank you very much for listening, for asking questions. And if there are more questions, then of course, I'd be happy to hear.
All right, thank you very much. Are there any questions?
Michael, intuitively, why are the corners less favorable?
Yeah, just who asked the question?
It's again Ron Pellet.
Okay, you know what? I'm going to stop my share, and then I'll actually be able to see the speakers. Okay. Hi. Why are the corners less favorable? So, okay, this is a great question. I don't have a clean answer for this because you might think that the corners should be the most favorable, right? They kind of. So, but here's like my attempt at answering this to myself because, yeah. So it's pretty clear that the middle of the board should be pretty bad because in the middle of the board, you're threatening like n spaces in both diagonals. You're threatening 2 n spaces. So you want to kind of move away from the middle of the board. And the question is, where should you move to? So first guess is the corner. Well, spaces in the corner only threaten n positions. And then when you look at the eventual density map, that's not the case. So what happens is that it turns out that like actually every single space in the top of the board has the same property, that it threatens only n positions. Okay, So, all right. So this tells us that some of the spaces in the top of the board should be more favorable than the middle. And indeed, like kind of the middle area of the top of the board is more favorable than the middle. But, you know, there's an additional constraint. We have to have a permutation matrix. So kind of like the probability mass on the top line of the board has to sum to 1. So if we're favoring any area on the top of the board, it's going to be instead of some other area. So I guess we're favoring the middle, and then the extra mass comes from the corners. Yeah, that's like, I mean, it's like, I guess what I'm saying is that it shouldn't be a surprise that there are some areas in the top of the board that are less favored than others. But I don't have a really clean explanation for why it's the corners and not, you know, some other space.
Okay, thanks. And thanks also for a great talk.
Thank you.
All right, are there any other questions? So I have a very small one, but you showed this paper by some physicists. So why do physicists care about this?
I mean, well, why do we care about it? Why do I care about it? I don't know.
Sure.
I mean, I think, okay, so I think for me, it was just interesting because it was like kind of like, it was clear there was a case where like existing methods and designs didn't quite work. I think for physicists and computer scientists, it's interesting because it's a good test case for, so the paper was really about was a particular method of counting things using Markov chains. And the two examples that they kind of showcased were counting n-Queen's configurations and counting Latin squares. I'd say that actually their count for Latin squares is not that accurate. So it's like, so I was a little bit surprised actually to see that their count for n-Queen's configurations was quite accurate.
Okay.
Another question, sorry. Can I understand correctly that your method is orthogonal to Borel and Kivash in the sense that if you were to study the toroidal problem, then this would not be very helpful because there the direct queenon is uniform, and then that would correspond to the random greedy algorithm, and the main obstacle is the absorption, and this is what they deal with. So they cannot use your ideas to make their proof simpler.
Yes, I think orthogonal is the right word here. It's like there are two parts of these proofs, random greedy or nibble and then absorption. And the difficulties are exactly in the opposite places. Yeah.
All right, thanks.
Right, are there more questions? That doesn't seem to be the case. In that case, thank you again, Michael. I will stop the